Hello everyone, this video is on functions, goes with 2.2 in the textbook. Remember to take notes as you watch so that when we go through it in class you can just add to your notes, and any questions you might have, write them down because you might forget them. Alright, so first, before we learn about functions, we have to learn about relations. And relations kind of hard to define because it's just any way of relating two quantities. That's it. So a lot of times you might see it like an ordered pair, like below. So you relate the set of x values 4 with, well, you relate 4 with 5, 6 goes with 2, 8 goes with -1, 10 goes with -7. You don't need an equation for a relation. It could be like a person's name and their age. So like Bob, 10, Adam, 28. Now, a function is a special type of relation, and that is when each value from the set of the first components, so that's usually called your domain or referred to as input, or the x value. So you plug something into the function and then every element in the domain is associated with exactly one value from the second component, which is called the range. So you plug something in and then something comes out. What comes out is considered the range. The output is another name for it, or y. So here is an example of a relation that is a function, and then we'll find one that isn't. So the one on the left, so like here's one where it's a Major League Baseball team and the league they're in. So the Yankees are in the American League, the Mets are in the National League, the Cubs are in the National League, the Indians are in the American League. Now, although there's no number involved, this relation is a function because every x value, in this case the teams, is associated with exactly one y value. So if I asked you, alright, what division or what league are the Yankees in, you could tell me American League. If I say what division are the Mets in, you could tell me National League. Cubs, National League. Indians, American League. There's no confusion there. Now, an inverse is when, and we're going to spend a whole section on inverses, but an inverse is when you switch the domain and range. So that's still a relation. So if I go American League and then Yankees and then National League and then Mets and then National League, Cubs, American League, Indians, this is no longer a function. Because now if I say, alright, what team is in the American League? Well, it could be the Yankees or the Indians. And when you have a function, that cannot happen. For every x value, there has to be exactly one y value. And in this case, we have one x value going to two different y values. So if you see repeated x values, it's not a function. Alright, you can have repeating y values though, and it's still a function. So you can also, some elements in y may not be matched with an element in x. So if you look at the picture on the left here, you know, if you have arrows from your domain pointing to elements in your range and one's left over, that's okay. Sometimes it happens. And two or more elements in x may be matched with the same y. So that's kind of like the example you just did, where the Yankees were in the American League and the Indians were in the American League. That's okay. You can have repeated y values. Also here, like f of x equals 2. So like that means f of 1 equals 2 and f of 2 equals 2. So if you were to make a map, you have 1 and 2 both going to 2. That's okay. That's still a function. As long as when you plug in an x value, you get exactly one y value, that's fine. Alright. And then, so how to test if something is a function. So if you're given ordered pairs, look for repeated values in the domain. So look for repeated x values. If they appear, then it's not a function. So if you have a set of ordered pairs and there's an x value that comes up more than once, the same one, not a function. If you have a graph, if there exists a vertical line that hits two or more points on the graph, it's not a function. So something like a parabola would be a function because no matter how many vertical lines you drew, it would only hit the parabola at one point. But if you had like a sideways parabola, that would hit the vertical line would hit the function at 2 points. Therefore, it's not a function. So that's called the vertical line test. If you can draw a vertical line and it hits the function at more than one point, it's not a function. If you're given an equation, solve for y, and if at some point you have to take the square root of y and you get y, the same y could be associated with two different x values, then it's not a function. So, sorry, I was trying to wipe something off the screen. So here would be an example of that. Something simple like x is equal to y squared. So if I was solving for y by taking the square root of both sides, that means x is equal to plus or minus root y. So if you think of like a map, you have positive root x and alright, let me just erase this part real quick. So now if you were to just take an x value, so for example, sorry to delete that last one, but just restart on the number 3. If you had something like x was equal to y squared, that's not a function, because if you were to solve for y, you would get y is equal to plus or minus root x. So if you had something like, alright, let me plug 1 in for x, so you take the square root of 1, and y now could be negative 1 or positive 1. They have one x value going to two different y values. Or like if you plug in 4 for x, so y could be 2 or negative 2. So see, you run into an issue there. So pretty much if you ever see an equation where, well, if you think of it in terms of x, if you had like a polynomial which you know had or like a quadratic, for example, and so it's like y is equal to x squared. You know that there's two values for x for every y value. So if you were to switch x and y and now have x equal to y squared, you run into this issue here where you have one x value going to two different y values. So in equations, if you see y being raised to even powers, it's not a function. Those are pretty much, other than that, you're just going to look at a graph and see if it passes the vertical line test. Alright, so one-to-one would be when every element in x is mapped to exactly one element in y. So f of x is one-to-one. So if you think of f of x equals x, so you have like, alright, plug in 1 for x, you get 1 for y. Plug in 2 for x, you get 2 for y. And that relationship goes for every value of x in this example. But if you think of something like f of x equals x squared, so if you plug in like, alright, here's x, here's y, if you plug in 1 in for x, you can get 1. But if you plug in negative 1 for x and you square it, you still get 1. So this is still a function, right? Because every x value is mapped to exactly one y value. Every x value has its own unique y value. But it's like, again, if you plug in like 2 and you square that, you get 4. But if you plug in negative 2 and square that, it's still going to be 4. It's still a function when this happens, but it's just not one-to-one. So f of x equals x, that's an example of something that's one-to-one. F of x equals x squared is not one-to-one. And you could check one-to-one by the horizontal line test. So if you look at this graph of f of x equals x, that's constantly increasing. No matter how many horizontal lines you draw, it's always going to hit the graph at exactly one point. Therefore, it's one-to-one. But if you draw a horizontal line on a parabola, at certain points, if you draw the horizontal line, it's going to hit the graph at 2 points. So horizontal line test, you can have it only checks if the function is one-to-one. You can have a function, so it's a function, so it passes the vertical line test, but also not be one-to-one and fail the horizontal line test. The point I'm trying to make, a failure of the horizontal line test doesn't mean it's not a function. It can still be a function. Alright? But special functions are one-to-one, and that's when it passes the horizontal line test. Or every x has exactly one y. And its own y. That y doesn't repeat. So, there you go. Explained again here. Horizontal line test, if it passes it, it's one-to-one. If it doesn't, because it hits the graph at more than 1 point, it's not one-to-one. Alright, determine if the relation is a function, and if it's one-to-one, then find the domain and range. Alright, so first, is this a function? So I check my x values and there's no repeated x values. So yes, it's a function. Is it one-to-one? Well, if there's no repeated x's and also no repeated y's, so it's one-to-one. If I were to make a map of this, 4, 6, 8, 10, and then a map, so there are my x values, there are my y values, and then graph the y values, so we'll graph them in order, -7, -1, 2, and 5. So 4 goes to 5, 6 goes to 2, 8 goes to -1, 10 goes to -7. So because there's one arrow coming from all the numbers in my domain, and each number in the range has exactly one arrow pointing towards it, that's another way to visualize that it's a function, and also it's one-to-one. Find the domain and range. The domain is a finite set of x values. We want to put them in order. So since it's a finite set, we use those squiggly brackets. So it's going to be 4, 6, 8, and 10. And then our range is our y values. So we want to put that in order. So -7 first, then -1, then 2, then 5. And then these squiggly brackets are for finite sets. Remember, we use like these parentheses for infinite sets, like all real numbers greater than 0, that'd be an infinite set. Or, greater than or equal to 0, we would put this hard bracket. But these squiggly brackets, which I don't draw too well, but let me try to draw it one more time, should look like that. Those are for finite sets. Alright, let's look at another example. Determine if it's a function. Alright, let's look at that first. Is it a function? No, it's not, because if you plug in 2, you get 2 different y values, so not a function. So therefore, it definitely can't be one-to-one. If it's if it's not a function, it's definitely not one-to-one. You can have a function that's not one-to-one, but one-to-one means there's exactly one x value for exactly one y value, and there's no repeats at all. You can still find the domain and range for this relation. So our domain would be -5, 0, and 2. So if 2 comes up twice, we just want to write it once. And again, we write these numbers in order from least to greatest. And then range, let's see, the lowest y value is -1, then 0, then 2, then 3. And let me fix that 0 right there. Not the best work, but there's the range. You can still find the domain and range. Alright, determine if it's a function and if it's one-to-one. So we have 4 unique x values. So if you plug in 1, you get 5, 2, you get 6, 3, you get 6, 4, you get 5. So that's a function. But since when you plug in 2, it goes to 6, and when you plug in 3, it goes to 6, this is not one-to-one. So if you were to draw a map of this, 1, 2, 3, and 4, and then also 5 is repeated as well. So since 1 and 4 both go to 5, that means it's not one-to-one. Same thing, 2 and 3 both go to 6. So like something in real life that would be one-to-one would be like every person and their fingerprint. That's a one-to-one relation because everyone has a unique fingerprint. But like someone and their name, right, their first name, there's a lot of people with the same first name out there. So that would be a function because everyone has their own name. Unless you have 2 first names, then that would be a counterexample. But let's assume everyone has 1 first name. If you were to map every person to their first name, that would be a function, but not a one-to-one function. All right, so here's another example. What we just did, that's a function, but not one-to-one. All right, our domain would be 1, 2, 3, and 4. And then our range would be 5 and 6. Make sure we put those numbers in order, and then make sure you use those brackets for finite sets. Alright. Quick shout out for Morgan. She's been asking me to shout her out in the video. I purposely put it in the middle of the video, so just make sure that she's watching it. So there you go. There's your shout out. Hope you enjoyed it. Alright, a couple more slides though. So determine if this relation is a function and if it's one-to-one. So, alright, is it a function? Well, it fails the vertical line test. You could draw a vertical line many different places. Here's one example that hits the graph at 2 points. Therefore, it's not a function. Like for example, if you look at this vertical line, if you plug in 0 for x, y could be 2 or -2. So that's an issue. For it to be a function, when you plug in an x value, there needs to be one exact answer with that x value. So it's not a function. And anything that's not a function can't be one-to-one. The domain, by looking at the graph, you look at all the x value that the graphs hit. So it looks like, it's kind of tough to tell, but that the lowest x value is -5. So our domain is going to be all real numbers greater than or equal to -5. As for the range, well, that looks like it's rising and falling forever. So it looks like it's going to hit every y value. So our range is going to be y belongs to the set of real numbers. So you can assume it's going to follow that same pattern. And I'll try to put arrows in my picture so you can assume it keeps going. If you ever see something like a point at the end of it, then you can assume that the graph stops at that point. But if it looks like it's going on forever, like this graph does, it gets cut off with the axes, it's probably going on forever. If you're ever not sure, you can just ask. Alright, couple more things. Oops, sorry. Function notation. So x is still x, but now y is going to be f of x. So function notation just makes life easier, right? When you type something like f of -1, that's the same thing as saying what is y when x is -1. Now, isn't that really annoying to write? Who wants to write that? So that's why we use function notation, especially in the world we live in with computers and codes, where function notation is super useful and used a ton. It's just a notation thing. It's just to make life easier. So if you're saying like, why can't we just use x and y? That's why. It's a fair trade-off. It'll take some learning at first, but literally, what you put in between the parentheses is x, and then what it equals is y. So that's why you might see like y equals f of x a lot of times. So if you see, in order to do something like f of -1 here, you need to know what the function is at first. So it's always going to be defined for you. So f of x is equal to 3 minus 2x. So f of -1 means wherever there was an x, you have to replace it with -1. So see how here there was a -1, so the -1 replaced the x. You don't put it next to the x, you replace it. So f of 0, alright, you plug in a 0 here, it's magically going to appear right there. So f of 0, if f of x is defined as 3 minus 2x, is going to be 3, because you do 3 minus 2 times 0 now. Then f of 2, well, now you replace x with 2. So it's like a portal. Like whatever goes through this door comes out that door. And then you just use it instead of x. You evaluate. Alright, this is called the difference quotient. So it's just an application of function notation. So it's used a lot in calculus. So we're going to get a little head start on it now. We'll calc preview. So first, in order to do this here, we need to know what f of x is. So we know what f of x is, so we can plug that in right there. To find f of x plus h, just like we knew f of x was x squared minus 4x plus 7, kind of running out of room here, but I'm going to make the best of it. F of x plus h means now we're just going to replace x with x plus h. And whenever we see an x, we're now going to plug in an x plus h. Then here, we're going to plug in a x plus h. So unsimplified, that's what f of x plus h is equal to. And then we can now take this and simplify it out. So FOIL out x plus h squared, which is x plus h times x plus h, which would be x squared plus 2xh plus h squared. And then this part would be minus 4x minus 4h and then plus 7. So we got this whole part taken care of. And then minus f of x, so minus x squared minus 4x plus 7. Make sure we use parentheses so we subtract the whole thing. Now we can cancel out in the numerator. We have an x squared here and a minus x squared there. We got a negative 4x there and a minus negative 4x there, and a plus 7 there and a minus 7 there. So in our numerator, we're left with 2xh plus h squared minus 4. And then, so that's from there, there, and there. And then don't forget about this h we're dividing by. So put that all over h. Wait a minute, I think I forgot something. This should be a minus 4h, I believe. Let me pause and double check that. Yeah, right over here. Apologize for that. When I crossed out, this should have been a minus 4h. And then, so this should be a minus 4h. Forgot about that. Alright, so now this h will cancel out with all of these h's. And you're left with 2x plus h minus 4. Alright, so that's just a fun application. Well, maybe not fun, but that's an application of function notation. Alright, so don't get intimidated by this f of x plus h. If you could plug a number in, like if I told you f of x was x squared minus 4x plus 7, and I said find f of 1, you plug 1 in for x, you plug 1 in for x, and you evaluate. Same idea, except now we're going to plug in x plus h in for x, and in for x. Alright, one more thing, and that's graphing a piecewise function, I believe. Having this technical difficulties here. Alright, last thing, how to graph a piecewise function. So a piecewise function is just literally two pieces of a function that you're only going to graph over certain intervals. So we're going to graph x squared plus 1 only over that interval when x is less than 0. So if you don't know what the graph looks like, it helps to plug in values and make a table. So if I were to make a table for x squared plus 1, you want to, even though we only care when x is less than 0, it's still worth plugging in what I call that border number, like plugging in 0 for x. Then you get like 0 squared plus 1 is 1. So we're going to put an open circle on 0, 1. And then we plug in other values on this interval, so like -1. So we get -1 squared is 1, plus 1 is 2. So we'd have the point -1, 2, and oops. So it'd be like right there. And then, sorry, it's tough to make a, there you go, point there. If you plug in a value like -2, -2 squared is 4, plus 1 is 5. So you have like -2, 1, 2, 3, 4, 5, be like up here. So this parabola will look like that. So we're only graphing half of it on the interval x is less than 0. And then for this part of the graph, I'm doing another color so you can see, that is the graph of x minus 1. So you're graphing y equals x minus 1, which would be this line, a line with slope 1, y-intercept -1, but you're only graphing it over the interval x is greater than or equal to 0. So that's another way to do it, to just graph the whole thing and then erase the parts you don't need. And then together, this red and green graph make this piecewise function. Alright, and we'll practice that more in class, but you're just graphing parts of a graph over certain intervals. Kind of like when we use Desmos, and we only, when you're doing the marble sliders activity, you're only graphing parts of the graph over those intervals. Same idea, except you have to graph it yourself. And when in doubt, making a graph, just make a table of values. And we're going to use these domain restrictions on the right to help us pick what x values we plug in. Alright, so I hope this video helped. If you have questions, bring them into class or post them as comments. Actually, I probably won't even read those, so shoot me an email or just ask in class. Do that. Alright, I'm going to stop talking now. Have a great night.